Hello everyone, good afternoon, and welcome to the last live interactive session for this course in this session. Okay, so today is the 13th interactive session, and today we are just going to summarize all the topics from the beginning to the end. That's all. We will try not to solve any problems or do anything, just we will discuss casually or just revise whatever we have actually studied um, in this course. Okay, so uh, till up till yesterday's discussion session we actually solved the problems, right? So we have solved most of the problems from all the courses, yeah, from all the topics, and today we are just going to summarize all of those. All right, and so let's start. So rough and rough, we have around 11 to 12 topics. So we will take approximately 5 minutes uh, in each topic, so that we can finish it up in 1 hour. And in this time, if you have any doubts, you may ask me anytime. You may interrupt and ask me anytime. Okay. So if you have any, if you have, even if you have the slightest doubt, feel free to ask me, and I will try to solve them. All right. So let us start. So the first thing that we studied was the soil formation, right? So there are various types of soil: igneous, sedimentary, metamorphic, all those things we studied, and how soils are formed from these rocks. Okay, so these are the type of rocks, right? So igneous, sedimentary, metamorphic, they are the main type of rocks. From these rocks, how soils are formed? So soils are mostly formed by weathering, right? So chemical or mechanical weathering, and then they are transported, residual, all these types of soil we actually studied, right? After that, we introduced soil as a three-phase system, right? The basic main concept of soil, that is, it is a three-phase system, right? So uh, it is composed of three phases, that is the solids, the water, and the air, isn't it? So it is composed of three phases. So based on this three-phase system, we derived some properties known as the index properties, right? So next we have the index properties. So what are the index properties? The test carried out in order to classify a soil known as classification test, and the numerical results, so the numerical values obtained from this test, are termed as the index properties. So various index properties we studied after that. Those are water content, void ratio, porosity, degree of saturation, right? Air content, percentage of air voids, then bulk unit weight, dry unit weight, saturated unit weight, submerged unit weight. All these types of unit weights we defined, isn't it? Then in specific gravity we define, right? After that, we studied the grain size distribution curve and how can we obtain the grain size distribution curve. So the grain size distribution curve actually we can obtain through sieve analysis, right? So there are two types of sieve analysis: dry sieve analysis and wet sieve analysis, isn't it? Dry sieve analysis and wet sieve analysis. So from there, actually we determine the grain size distribution. Okay, so how do we do the sieve analysis? That also we studied, right? That also we discussed. Then this dry sieve analysis, we studied the hydrometer analysis. So how do you use the hydrometer to determine the fine fraction? Okay, to determine the gradation of the fine particle fraction, right? For that we use the hydrometer, so that we also discussed. Okay, so then there we studied various corrections, the temperature correction, the dispersing agent correction, all these corrections in hydrometer reading. After that, we defined the D10 size, which is effective size, CU size, CU, LCC, coefficient of uniformity, coefficient of curvature. Those are actually needed to define the granular soil as well graded or poorly graded. After that, we define the consistency of clays from the that is the degree of firmness, right? Degree of firmness, and then we define the Atterberg limits. That is the liquid limit, plastic limit, shrinkage limit. All these things we define. And how to find out liquid limit, plastic limit, that we also saw. And what are some index property and some other properties in plasticity index, relative density, all these things. Then we proceeded to solve the problems, right? So those were the basics, the main basic of this soil mechanics. So these things actually, as you know, we had used all throughout the course. These basic properties we had used all throughout the course. Then in the second week, what we studied the soil classification, right? So yesterday also we recapitulated soil classification by solving a problem, isn't it? So we studied soil classification. So uh, how do we classify soil? So there are various systems, USCA system, as to ISSCA system. So we mostly focused on the Indian standard soil classification system, which divides the major soil into these major groups. And how do you identify each of these groups? Actually, we saw, right? Right. So if the fraction of soil more than 50% is passing through 4.75 mm, and less than 50% is uh, passing through 75 micron, then the soil is coarse grained sand, right? So like this we determined, we divided the granular classification in many parts, right? So this is the summary of that. Then we saw how to classify the fine grained soil, right? Fine grained soil. Okay, so those, for that we need to use the use this a line chart. Okay, a line chart. Okay, the equation of the a line that is written here, 0.73 wl minus 20. So if the soil plots above the a line, then it's a clay. If it plots below, then it's a silt. And also apart from that, we discussed various uh, dual nature conditions, right? So dual nature conditions where we have to dual classification we need to use, dual symbols. Okay, so all these things we summarized. I am not going in one by one, step by step in detail. After that we also saw what soil structure is, right, and what specific surface is, and how actually this influences the soil behavior. Then we saw what are the main minerals that form the soil, and how what is the structure of those minerals. Those things we show what are the basic constituents, how those minerals are soil minerals are formed, that we actually saw, right? So what are the basic minerals? Kaolinite, morillonite, and elite. So these are the basic minerals which form a fine grained soil, right? So we studied this. right? So that was also, after that what we did, we solved many numerous numbers of problems related to soil classification. And I hope that this is clear to you, because this thing we will be needing throughout your life, right? Should not forget the soil classification. Okay. Then in the third week we studied about uh, soil compaction, right? We studied about soil compaction. So what is soil compaction? Soil compaction is a densification of loose soil, right? So how do you generally do soil compaction in the field? By say roller, by using road rollers, by using tamping, all these things, right? So what is soil compaction? The densification of soil by removal of air. So what you are doing, you are removing the air by uh, providing some external mechanical effort, due to which what happens, the air in the soil matrix actually gets removed, and the soil grains actually attain a more denser configuration. Okay, that is what soil compaction is. So water is added during this compaction process. So what does water do? Water acts as a lubricant. Okay, water acts as a lubricant. Okay, so this is the this bell curve that you see, that is the uh, what to say, typical compaction curve that you obtain. And at a certain point you have the maximum dry density that you have achieved, that is the maximum dry density. And that maximum dry density actually corresponding to a water content, and that water content is known as the optimum moisture content or optimum water content. Okay. So to do this compaction, which compaction test to find out the maximum dry density and the water content of a particular soil, we use the Proctor test, right? So we use this Proctor test, standard Proctor test, to actually determine the OMC. Okay. So what is this Proctor test? This Proctor test says we have a mold of certain volume, a certain size, and what we need to do, we need to place the soil in particular number of layers and then tamp it. Okay, so that is so there are two standard Proctor test and there is another heavy compression. So in both the cases, the hammer weight, the number of layers, the number of blows, all these things differs. That means the compactive effort differs in both the cases. Okay, then we define the zero air void line. So what is the zero air void line? Zero air void line is the theoretical maximum line of maximum dry densities, right? So that is the theoretical maximum dry density that you can achieve. Okay, that gives the zero air void line. All right. So generally the compaction curve is always it never touches the zero air void curve. It is always below that. Okay, then we studied the other various factors that affect the soil compaction. All these things we actually revised. And as I was saying, there is a modified Proctor test, where in this modified test the compacting effort is higher because the number of blows are higher, number of layers are higher, and all those things. Now, field compaction, how do we compact in field? Using rollers, right? There are various types of rollers, as I mentioned here. Okay, and how do you actually measure the dry density in the soil? So there are various methods, sandstone method, available with the nuclear method. So we discussed the sandstone method in detail, and you can read about all other methods also in your standard textbooks. After that, we introduced a permeability topic. So what is permeability? So water flows through soil with the presence of interconnected uh, voids, right? So how much water, how much, how easily the soil is allowing the flow of liquid through it, that is defined by the permeability coefficient, right? So we generally start from the uh, hydraulic gradient, then we define the Darcy's law, that is V is proportional to the hydraulic velocity of flow is proportional to the hydraulic gradient, and then we introduce the constant of proportionality, that is the K, that is the coefficient of permeability. Just a second. Just a minute. I'm getting a call. Just give me 1 minute. Yeah. I'm very sorry for the interruption. So let us continue. So water flows through the present interconnected voids. From that is what permeability is. All right. So we define the coefficient of permeability, right? Then we define seepage velocity. So the seepage velocity is always greater than the superficial or the average velocity. Okay. That also we derived. We saw that. We saw defined the relation V is equal to V by Vn, and there are various factors that affect hydraulic conductivity. Okay, then we solve the problems. All right. Then in the fourth week, in the starting, we saw some tests that are used for the determination of hydraulic conductivity, or the laboratory determination of hydraulic conductivity. So the basic tests are this: constant head test and the flowing head test. So the constant head test generally we use for granular soil, and the flowing head test we generally use for uh, fine grained soil. And for both these tests actually, what we did, we derived the expressions for the coefficient of vulnerability. So for the constant test, you can see this is the expression K is equal to QLAHT, where Q is the flow, L is the length of flow, A is the cross-sectional area, H is the constant head, and T is the time. Okay. Then we the term for the derive the expression for the falling head test, right? So in time t1 to t2, the head falls from h1 to h2. Using that, we derive, that is the k equal to ahl at ln of h1 by h2. Okay. Now, apart from a test, there are some empirical relations also, which relate the coefficient of permeability with several other parameters. So those we discussed briefly. Post that, what we did was we derived expressions for equivalent hydraulic conductivity, right? Equivalent hydraulic conductivity in horizontal direction and equivalent hydraulic conductivity in vertical direction. So those you can see here clearly, right? Now one more uh, important thing, how to determine hydraulic conductivity in the field. So one of the most common methods is this pumping from well methods, right? So we discussed this pumping from well methods and how this pumping method is actually used to determine the hydraulic conductivity. Then what we did was we derived the expression here. Okay, so this was all about permeability. Then what we did, we discussed about the seepage. So for seepage, what is seepage? Seepage is nothing but the what? Seepage is nothing but strain the flow of water. Okay, that is what seepage is. Seepage of water. So in seepage, what we did was we actually tried to derive the uh, mathematical differential equation that actually describes the flow of this fluid in the soil mass, right? So that we define. So it where for 2D flow we derived this Laplace equation, that is kf dou square h by dou square h by dou x square plus kz dou square h by dou z square, where kx and kz are the coefficient of permeabilities in the x and z direction. Okay, for isotropic soil, kx and kz will be same, and for that we can write this property. This we can uh, write this Laplace equation, and for 1D flow we can write this. So we saw all this stuff. Then a solution of this um, solution of this flow, what to say, this Laplace equation is nothing but the flow net. Okay, the solution of the Laplace equation is nothing but the flow net. Okay, so there are very some properties of the flow net, so that the flow these lines are actually orthogonal to each other. They cut each other at 90 degree. Okay, and they form a family of curves. So flow channel, there are flow net, there are two lines. One is the equipotential line and the other is the flow line. Okay, so all those things we saw. Also, we derived various expressions that how using the flow channels and the equipotential lines, equipotential drops, how can we actually determine the flow. Okay, so first we draw the flow net, and from that we find the number of flow lines, number of drops, and from that what you can do, you can actually calculate the amount of flow that is happening. Okay, then as usual we solve many problems from this topic. Okay, so I hope that these problems are clear to you, and I have solved each one of the problems, but I still suggest that you solve all these problems once again by yourselves. Okay, yourself, only then all the concepts will be clear, and also if I have made any mistake, you can correct it. Okay, so you should check all the results by solving it yourself. Okay, solving this yourself. So then we discussed how to draw the flow nets, right? So several trials are needed to draw a flow net. So here I actually showed you what is the how equipotential line, what are the boundary equipotential lines, what is the boundary flow line, all these things we saw, right? And for anisotropic soil, so what if the soil is anisotropic? Okay, kz and kx are not same. At that time, how to approximate the Laplace equation, that also we saw. Okay, so flow net is regularly used for determining the uplift pressure under hydraulic structure, and regarding this we also solved some problems where we determined the uplift pressure and all from the flow net. Okay, so after that we started saw the seepage throughout them. So these were actually derived in detail in the class. Uh, in the lecture by Professor Ghosh. So I think this all should be clear, right? So how this seepage through an earthen dam is actually calculated, that we saw. That was all about that. And then we understood what are in situ stresses. So this is also one of the most important concepts. It is the concept of effective stress. So what is effective stress? Effective stress is nothing but the stress that is carried in the grain to grain contact. Okay, that is carried by the grain to grain contact. Okay, that is the effective stress. And total stress is composed of the pore water pressure or the neutral stress and the effective stress. Okay, so that those how this concept of effective stress actually comes, that we saw discussed actually. Then we saw these cases where various cases of this seepage condition, no seepage, downward seepage, upward seepage, all these things we discussed, and total stress for water pressure and the effective stress we plotted. And we saw that for upward seepage, what happens? The effective stress actually gets reduced. Okay, effective stress actually gets reduced due to the effect of upward seepage. Okay, and that actually gives us a critical condition. If this effective stress becomes zero, if this effective stress becomes zero, the hydraulic gradient at which this effective stress becomes zero is given as the critical hydraulic gradient. And what is critical hydraulic gradient? This critical hydraulic gradient actually leads to a piping condition, and this critical hydraulic gradient varies from zero point 0.9 to 1.1, and it is given by G minus 1 by 1 plus C. Okay. Yesterday also, if I remember, we had solved one problem regarding this critical hydraulic gradient. Okay. Then we derived a term called seepage force. All these things we saw. Yeah. And then we solve the problems. Okay, so we solve many problems. Some problems we solve from this effective stress part, calculation of effective stress, right? Calculation of total stress, effective stress, for water pressure we saw. And then we calculated some problems regarding this uh, seepage thing. Okay, seepage in through a dam, those things we saw. Also, you can see we solved many problems where we found out the uplift pressure below a dam. So all these things, I think these are clear to you. Okay. After that, we define capillary rise and how to calculate the height of capillary rise and what the capillary rise is, that we will discuss. And what happens to the effective stress in this zone of capillarity, that we also saw. Due to the suction, the effective stress in that zone actually increases. Okay, the pore water pressure becomes negative, that leads to the increase in effective stress due to the suction. Then we start introduce the main one of the main topics, that is the consolidation. Okay, that is the consolidation. We saw what consolidation is one of the most important topics. We uh, discussed consolidation using the spring cylinder model, right? So what happens initially when you apply load and you are not allowing drainage, the whole load is actually transferred to the water for a saturated soil. Okay, and remember that consolidation is defined for saturated, fully saturated. As soon as you open the valve, water starts coming out and the load is transferred from the water to the spring. That is the soil grains. Analogy for the spring is the analogy for the soil grains. So whatever the effective stress actually increases. So we saw all the boundary conditions for this. Then we discussed the 1D consolidation test, one dimensional consolidation test. So how we can do the test we discussed, and how can we actually get the curves that we need to determine the consolidation parameters that we discussed. So this is the basic 1D consolidation test result for each load. Okay, for particular load, so deformation versus in the time log scale you can plot like that. So first we have the primary consolidation, then we have the secondary consolidation. The primary consolidation only contributes to the maximum settlement. So consolidation, the first is the initial compression, that is the elastic loading that you put, elastic settlement, initial compression, then you have the primary consolidation, and then you have the secondary consolidation. So how to generate these void ratio pressure plots? Okay, how to generate a typical void ratio pressure plots we saw. There we defined various coefficients, the coefficient of compressibility, compression index, coefficient of volume change, swelling index, coefficient. So among these, this AV, CC, MC, we regularly we use to solve the problems. These concepts we regularly use to find out the consolidation settlement, if you remember. Yes, so we solve numerous problems. So these problems regarding this finding of the void ratio pressure settlement curve or void ratio pressure curve, I told you that you should actually be very careful when making this table. Okay, you should be actually very careful while making these tables, else you are going to do mistake. Okay, generally students do mistake here only. Okay, so you should be very careful on which void ratio or from which void ratio you are calculating the next void ratio and all those things. You should be very careful. All right. And other things we already discussed. Okay, so these also we discussed, right? So we generally take a 2:1 distribution of load, and that actually we take as the increase in load. From to that load, how much settlement is consolidation settlement is occurring, all these things we calculated. Okay, so yeah, so next we have this E versus pressure plots. So this we all, so that is what you need to calculate, right? From the 1D consolidation test, right? So that we saw. So there is a loading curve, unloading curve, rotating curve. So what is the consolidation pressure we discussed, and how to determine this pre-consolidation pressure, right? That we discussed using Casagrande's method. So we need to draw a straight line first, then we need to draw a this tangent, then you do the angle bisector, then you need to extend the straight portion backwards at the point at which it intersects. That will actually give the pre-consolidation pressure. So for settlement calculation, there are various uh, what to say. There are various conditions or various circumstances that might come. So those are discussed here. Then discuss about secondary consolidation settlement. So secondary consolidation settlement is extremely low. So it happens after the primary consolidation settlement due to the plastic settlement. Okay, so plastic readjustment, sorry, some plastic readjustment. So it is actually very low. Then we discussed the Terzagh's one-dimensional consolidation theory, from where we defined the basic consolidation equation, dou u by dou t equal to cv dou square u by dou z square. That is the basic consolidation equation. From there we defined the coefficient of consolidation, which is nothing but k by gamma wmb. And from there what we did, we actually saw this curve from this tv, this time factor, which we saw in the solution. So the solution of this Terzaghi's consolidation theory, where u is the pore water pressure. So this pore water pressure is actually given by this. Okay, in this term you can see this time factor here. Okay, so this time factor actually relates to the time, how much time it will be needed for attaining a certain degree of consolidation, right? So this is one of the most important expressions. Tv is equal to cvt by drainage square, drainage path square. Okay, then we solved many problems from this. We settlement calculation, we solved problems related to settlement calculation. Then we solved problems related to this time, how much time will be required for attaining a certain amount of settlement. All these things we solved. And yesterday also we solved one problem. So if you remember, if drainage path is, if I told you emphasized on that, if drainage path actually reduced by half, then what happens, the time reduces by 4 times. The time to attain a particular amount of settlement actually reduces by 4 times. So these were all that we solved. We solved many problems actually. So generally, if we have a certain like this, so what we do, generally divide the layer into certain small layers. So we'll calculate the consolidation of each of these layers and then add it up. So this is generally done. You can do using write a small easy computer code, where you can actually find the optimum number of layers that you can need to divide the soil layer. Okay. So say uh, first you divide into 4 layers, then you calculate the consolidation settlement, and then you divide it into 5 layers, then you calculate the consolidation settlement again. So after that, if you find that the difference between two is not greater than some tolerance value, then you can say that this is the optimal number of layers. Else you can take more number of layers. So so using a small computer, easy computer code, you can actually do this, find this. Okay, so these are all that we did. After that, we started one more important topic, that is the shear strength of soil, right? So what is the shear strength? Shear strength of a soil mass is the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. Okay, so that is what, how we define the shear strength. One of the one of the main basic criteria is the Moore Coulomb failure criteria, which defines that a shear strength, so the shear stress at failure in a soil mass is a function of the normal stress. Okay, it is a function of the normal stress. So that is generally a curved line, that is generally not non-linear, but then it was linearized using the Coulomb's theory, where the shear strength was given as shear strength at failure, or the shear strength or the shear stress at failure is nothing but tau f is equal to c plus sigma tan phi. But c is the cohesion of the soil, phi is the friction angle, and tan is sigma is the normal speed. Okay, c is generally zero for sand or inorganic silt. But then we saw the this Moore circle. We saw this Moore circle and how actually we get this failure line. Okay. After that, from the mode circle, what we do from the using the mode circle, we actually determine one of the one more important expressions, that is the relation between these. The mode column failure criteria is nothing but the mode column failure criteria in terms of the principal stresses. Okay, sigma 1 and sigma 3. Okay, that we determine. Okay, sigma 1 prime equals sigma 3 prime tan square 45 plus 5 prime by 2 plus twice c prime tan 45 plus 5 by 2. So now you can see, now if you see what is tan 45 plus 5 by 2 is nothing but what? Kp, right? Kp. Then one of the simplest test to determine the shear strength parameters, that is C and phi, is the direct shear test. So what we do, direct shear test, we shear the soil mass along a predefined failure plane. So we put a normal force and see where the failure is at what shear stress the failure is actually occurring, and then we do that at different normal forces, and then we plot the curve. So we get, from there we can get the C and phi. Okay. So like this, to plot the points, we join the line, from there we can get the C and phi. So there are certain limitations of the direct shear test. So what are they? The shearing plane may not be the weakest plane, because we are already predefined. Okay, right? That predefined plane might not be the weakest plane, and the shear stress distribution of the shear surface specimen is not given. So these shortcomings are actually overcome in the triaxial test, where we use a cylindrical soil sample. Okay, the cylindrical one, we apply confining pressure and then do the test. So there are various types of triaxial test we discussed in detail: CD test, CU test, UU test, consolidated drain test, consolidated undrained test, and unconsolidated undrained test. So what are these tests? These tests are nothing but this test contain of two stages. So the first stage is the consolidation stage, and the second stage is the the shearing stage. So in the first stage, consolidation stage, what happens, we have to in CD and CU test, what we do, we open the drainage valve, and then we allow the consolidation to occur at a particular isotropic this cell pressure. Okay, and then, but in the UU test we do not do that. And in the second state, in UU and CU test, what we do, we close the drainage valve, we do not allow drainage, and then we increase the deviating stress or the axial load. And in CD stress, what we do, we actually, in the shearing stage, we keep the drainage valve open, and that these tests should be conducted very slowly, else what will happen, pore water pressure will going to generate. So CD test is actually very slow, it's very time taking, and we have to do it very slowly. Okay. So UU test we discussed in detail, and how the mode column will be obtained in the UU test, that also we saw. Then you CU test we saw, also discussed about the CD test, and also we saw that for normally consolidated soils, the C is generally 0. Okay. After that, we solved numerous number of problems regarding this. So some basic problems we solved using the shear strength, this direct shear properties. Then we solved some problems from uh, this triaxial test. Right, we solved many problems using this triaxial test parameters, triaxial test results. Right. So everywhere, most of the time, this basic equation sigma 1, this equation is actually used sigma 1 to sigma 3 tan square 45 plus 5 by 2 plus 5c tan 45 plus 5 by 2. So you should always remember this basic equation. Okay. Then we discussed about the this pore pressure parameters, right? So we discussed about the pressure parameters. So what are these pore pressure parameters? So these pore pressure parameters we discussed in detail. So there are two pore pressure parameters, A and B. So the B pressure. B is really calculated in the consolidation state. So, this parameter actually shows us that whether the soil is completely saturated or not. Okay, so if B is almost near to equal to 1, very close to 1, then we can say that the soil is saturated. Okay, soil is almost saturated. So and then we define this A parameter. So this A parameters is generally seen in the CU test. So this A parameters also we defined. This is nothing but this is nothing but it relates the pore, pore water pressure increase due to the increase in the deviatic stress. Okay. Then we saw what stress path is. What is stress path? Stress path is nothing but the locus of points representing the stress test during the progressive test. So as you do the test, how the stress states are actually progressing, how the test is actually progressing ahead, that actually gives us the stress path. Okay, so stress path can be understood from the P and Q easily. So what is P? The average mean stress, and Q is nothing but the dielectric stress. Okay. So it is discussed this also in quite a detail. Okay, then we saw that from the this is from the PQ. From the PQ, if you know P at failure and Q at failure, from there also we can get the C and 5 values. Okay, that also we saw. And these stress paths we saw for CD and CU test for NC clays. So how these pore water pressure parameters are actually derived, all these things we saw. And why B is equal to 1. As I said, for saturated soil B is equal to 1. Now why this B is equal to 1, that also we saw. And why B is equal to 0 for dry soil, that also we saw. Then we solved again many problems regarding this. Okay, so these problems we can basically solve from the triaxial test results, right? The problems are quite easy, just you have to plot the write everything, tabulate everything properly, and then plot the mole samples and get the results. Okay. Then one more large topic, one more principal or major topic in this soil mechanics is the earth pressure theories. Okay, so there are three earth pressures: earth pressure at rest, active earth pressure, and passive earth pressure. Right, active earth pressure, passive earth pressure, and earth pressure at rest. So we defined all these things. So what is earth pressure at rest? When the wall is not moving, that time what is the pressure? Then what is active earth pressure? When the wall is actually moving away from the backfill. At that time, whatever pressure is generated, that is the active earth pressure. And when the wall is actually moving towards the soil backfill, at that time we have the basic pressure. Okay. So from the Moore circle, how we actually get this active pressure and passive pressure that we saw. The active failure wedge actually makes an angle 45 plus 5 by 2 with the horizontal, and the passive wedge actually makes 45 minus 5 by 2 with the horizontal. Lateral earth pressure coefficient at rest is nothing but mu by 1 minus mu. This we got how? Because the lateral strains are 0. From there we got this. Then we actually uh, derived the Ka and Kp. Okay, Ka and Kp. It is the coefficient of earth pressure at active inactive state and the passive earth pressure coefficient. So all these things we derived, and how we derived were just using the from the basic equation of the Moore column failure envelope in terms of sigma 1 and sigma 3. Using that we actually got this. Okay, from there we got this. So this is the expression. These are the expressions for the granular soil, right? For C is equal to 0. And later after that, we in the later stages we also saw for C5 soil what is the case, right? So there is the extra term minus twice C root over K that comes in terms of in case of active state, and there is a term plus twice C root over K that comes in terms of the passive state that we saw. So what are the stresses in different conditions we saw, and this should be actually crystal clear to you because we solved many problems. Yesterday also we solved, before that week also we solved, in this week 10 also we solved. So we solved many problems regarding this earth pressure theories, right? So it should be very clear to you. All these concepts should be very clear to you, and you should practice it again and again. So active earth pressure, you can see, as I said, in cohesive soil we have this term minus 2ic by root over alpha, which is nothing but minus 2ic root over Ka. So these things we saw, and in case of passive pressure it is plus. Okay, then what we did, we solved some problems. Yeah. All were basic problems only, not that. Yeah. And this problem I told you to do in homework, and I hope that you have done this. Okay, I won't be solving that. You should do this by yourself. All right. And then in the week 11 we solve problems from this stresses in soil and Coulomb's earth pressure theory. So as I said, Coulomb, what does Coulomb's earth pressure theory do? Coulomb's earth pressure theory actually considers that there is some friction between the wall is not smooth. There is some friction between the backfill and the wall. Okay, and actually the Coulomb earth pressure theory actually gave a generalized expression. If the backfill is say, if the wall is say inclined, wall is not straight, it is inclined, or if the backfill is not straight, it's inclined. So for all these various conditions, the earth pressure theory actually gave Coulomb. And then we saw the strategies in soil using the Bosenic theory, Westergaard's theory. We discussed the assumptions of both these theories and how the expressions are actually derived. And then we solved the problems regarding that. Okay. So first we solved problems related to earth pressures. Many problems again. We solved huge number of problems regarding earth pressure. And then we see, you can see for inclined backfill how to that also we solved. And then we solve problems for the Bosenics and Westergaard theory. Okay, so due to the loading on the soil, how to calculate the stress increase in at a certain depth in the soil mass, that we saw. Mostly these are very easy direct formula based questions, right? Nothing extraordinary, nothing very difficult, direct. And this is a very lengthy problem. Yesterday also we solved one problem regarding this. So this problem while solving you should be very careful while you put the values in this big expression for k. Okay, else you will make mistake. You should correctly choose this L value, mn values. You should calculate very correctly, and then you put all the values very slowly in this k expression, then you calculate them. Okay, so that was all. And in the yesterday, so we discussed only, we solved same similar problems, right? Right. So that was all. Okay. So uh, this is all in this course, right? This is all about this course. And we are going to actually end. Okay, we are going to end this course with this. And I hope that uh, all these things were, all the concepts that were discussed were actually clear to you. And as I said, if you have any doubt, please feel free to contact me anytime. Some of you had also uh, contacted me over email. Okay, so if you have any doubts, please feel free to contact me. I will try my best to clarify your doubts. And uh, I hope that all the topics starting from the index properties, what is soil index properties, compaction, like seepage, consolidation, permeability, earth pressure theories, shear stress, all these topics were actually you understood all these topics very nicely. And we have also solved a huge number of problems from all the topics. And I am hopeful that you should be able to perform well in your exams. And I suggest that you practice more and more problems. You take various. There are many good textbooks such as Gopal Ranjan, and we have by VNS Murthy. Uh, then many more, there are many more. Okay, many more textbooks are there. So the more problems you solve, the more confidence you will get for the exam. Okay, because in exam what you need to do, you need to solve the problems very fast, right? And moreover, you won't be having your this physical calculator there. You have to use the online calculator, so that actually makes the process a little bit slower, right? So I suggest that you actually uh, practice more and more problems. And while you practice, you use that online calculator. So that link is actually given in NPTEL website, so you can use that uh, link from the NPTEL announcement section, where the details about the exam is given there. That calculator link is given. So what you do while you practice the problems, I suggest that you use that calculator. Okay, so that you can get familiarized with the calculator, and while you solve the problems it becomes easy for you, because in a very short time you need to do the right. So do the exam, right? So write the exam. So you practice more in version, read all the concepts very with all the basic concepts very nicely, very properly, and everything should be clear in your head. And again and again I am saying that if you have any doubt, uh, feel free to message me or mail me. I will try to solve it. And it was wonderful meeting all of you in this course, and I hope that all of you have enjoyed all the throughout this course. So a lot of effort was actually put from the whole NPTEL team for this course. So you had the lectures, then you had two separate discussion sections for sessions for this 12 weeks. Okay, so we have lot of content that was put together for you, so that you can actually learn the concepts and perform well in your exams. Okay, and I hope that you the concepts that you have learned in this course you will remember throughout your life, throughout your civil engineering career. And if you have any doubt at any point of time, please feel free to contact me. I will be more than happy to assist you. Even after the exam, if you have any doubt, then also you can contact me. All right. So thank you so much for attending this course, and all the very best for your exams. And I'm hopeful that you all will do very well. And thank you for attending all the discussion sessions also. Okay, and please put your feedback in the feedback links that were shared by uh, NPTEL. Okay, so thank you, and uh, have a very good year ahead. And next year and in the next sem, if you take um, if you take any NPTEL course regarding this geotechnical engineering, you might meet me again. Else, if you want to know anything from me, you can mail or write to me anytime. Okay. So with this note, we will end the course for this session. And with this last summary session, we will also wrap up the interactive session for this course. And thank you so much for attending all these 13 lectures were actually, or the 25 hours that we have spent together, but very much enjoyable to me. And I hope that you also enjoyed this course very much. Okay, with this we will end, and thank you so much for attending, and have a very good day and a very good year. All the best for your exams. Thank you.